Okay, so when we're looking at chemical equations, there's a few things we're going to do, and this is what we're going to be doing in lab next week. On Tuesday and Thursday, we're going to be doing this in lab. Okay, so if we look at this, here's our objectives. There's kind of a lot of them. It's a long chapter. We're going to be here for a while. So the first thing we're going to do now is we're going to look at writing equations and classifying reactions. So that's our first task that we're going to do. The next part is doing everything we just learned in chapter 6 and applying it all to this. Okay, so when we look at a balanced chemical equation, we always have the reactants on the left and the products on the right. So we've got our reactants over here and our products are over here. So that's pretty standard in our balanced chemical equation. And when we look at this, we can write these in a couple different ways. So CH4 can look like this, and this is what we did in lab in our Lewis structures when we created the little models. Both of those are correct. So again, here are our reactants, and here are our products. And a chemical equation is just writing the chemical reaction, the chemical change that we talked about at the beginning of the semester. Now, the coefficients is the number of reactants. So do you see how there's nothing in front of the CH4? That means there's one CH4, two oxygens, one CO2, two waters. These are called the coefficients. We're going to talk about why these are important in the next couple minutes, what these coefficients are. So remember when we talked about if you've ever heard the law of conservation of mass, mass can't be created or destroyed. That's why we need those coefficients, because those coefficients make our reaction what we call balanced. So we can't destroy or create matter. So if we look at this equation right here, if we look at, for example, our carbon, we have one carbon on our reactant side, and we have one carbon on our product side. We have to have the same number of atoms in the reactants as we do the products. They don't need to be in the same arrangement, but there has to be the same number of atoms. So if we look at hydrogen, if we look at our reactant side, we have 4 hydrogens. Oops. Well, oxygen, we have 4 hydrogens. And if we look over here, we have, and now this part is really important. You see there's a 2 in front of the hydrogen and a 2 after. So this is 2 times 2, which means 4 hydrogens. So we have 4 hydrogens in the reactants and 4 hydrogens in the products. Now, if we look at oxygen, how many oxygens are in the reactants? 4, because 2 times 2 is 4. Now, if we look here, we have 2 oxygens, and then this distributes, so we have 2 oxygens, so we have 2 plus 2 oxygens, which is a total of 4 oxygens in the products. And so this is a balanced chemical reaction because we have the same number of each atom on the reactants and the same number of each atom on the products. That's what makes it a balanced reaction. And again, the reason we do that is because we can't destroy or create matter. It has to be the same number of each. Okay, now when it comes to balancing, there's a couple of important things that we need to remember. Okay. You can't change the reactants or products. What do I mean by that? You can't go, oh, look, I need another oxygen, so I'm just going to add a 2 here. No, you can't. Nope. Nope, you can't do that. Nope, you can't add a 2. You can't change the reactants or products. The other thing you can do is you can't go, oh, I need another oxygen, I'll just add 1. Nope, you can't just add reactants or products. Can't do that one. The other thing is we don't use multiples. So you see how there's a 4, a 2, and 4 here? We need to write that as simple as possible. So we would simplify that to a 2, a 1, and a 2. So we always write it simple. When we're balancing reactions, the only thing we can do is change the numbers in front of the molecules. That's all we can do. We can't do anything else but change the numbers in the front. Now, when it comes to balancing, some of you are going to have what I call the balancing gene, which means you can just see it. You are blessed. The rest of us do not have it. Okay, you're going to know in the next 5 minutes if you have the balancing gene, because I'm going to go through a way to balance and you're going to be like, I don't need to do that. I can just see the answer. Awesome. We don't like you. So the rest of us are going to take some time to learn how to do balancing. There is no magic trick to balancing. The only thing I'll tell you is have an eraser. Don't use a pen, because you will do a lot of erasing. Even if you're good at it, even if you have the gene, you will still probably do a fair bit of erasing. Okay. So let's look at this equation here. So if we look at this, the first thing we always do is it balanced? Well, if we look here, we have 4 hydrogens and we have 2 hydrogens. That's not balanced. No, not balanced. Okay, let's look at our oxygens. We have 2 oxygens and 2 oxygens. Oh, well, our oxygens are balanced. That's awesome. But our reaction is not balanced. So how we do this, I'm going to show you kind of like a way that you can do balancing. Now, this one's pretty simple, so you can probably just see it. They're going to get more difficult. So how can we make it so we have 2 oxygens over here? Sorry. 4 hydrogen. Well, I just gave you the answer. How can we make it so we have 4 hydrogens over here? How can we make 4 hydrogens over here? What can we do? We can just add a 2 here, right? So if we add a 2, now we have 4 hydrogens and 4 hydrogens. And so now when we look at it, it is balanced. So we added this 2. So when we look at our hydrogens, let me see if I can make this smaller again. There we are. When we look at our hydrogens here, now we have 4 hydrogens in the reactants and 4 hydrogens in the product. So now it is balanced. And we didn't mess up our oxygen, so that's good. Okay, so now let's try one. It's a little more tricky. Sometimes you're going to be able to see that if you have the balancing gene, you're going to be able to see this answer way faster than I can do this problem. You don't ever need to show your work with balancing. It's whatever works for your brain for balancing. That's how you balance. However works for your brain is good enough. Now, there is a little hint when it comes to balancing that you can use, and that hint is if a polyatomic ion is in both the reactant and the product, you can treat it as one thing. Okay, what do I mean by that? Here is the polyatomic ion named sulfate. Here is the same exact polyatomic ion, sulfate. Because the same polyatomic ion is in the reactants and the products, we can treat it as one single thing. So now if you have trouble with balancing, here's a method to help you with balancing. The first thing you do is you write down everything in the reaction. Okay, so first we do sulfates. There's 1 sulfate over here, and there's 3 sulfates on this side. Okay, now let's do aluminum. How many aluminums on this side? 1. How many aluminums on this side? 2. Here goes my computer doing its thing, sorry. Shrink back down. Just does this. One second. Usually, yeah. There it goes. It's like, no, I don't want to play anymore. It just does this and it just shuts off. So let's just reopen that again. So when you're doing the balancing, you identify how many of things are on each side and you kind of like make like a table. So that's kind of the key to balancing. Hold on, let me go back to it. You just shut everything else off. We should be good now. Okay. All right. So when we look at this here, we've got one aluminum on the left, one aluminum on the right. And we look at iron, we have one iron on the left, one iron on the right. So this is everything in our equation. So when we're looking at a strategy to do balancing, this way works really, really well. So now we need to decide. Now where you start here is totally your option. Let me see, where did I start? I started with sulfates. Okay, so we need to get the same number of sulfates on each side. And we have 3 on the products. We want 3 on the reactants. So if we put a 3 in front here, we multiply this by 3. Now we have 3 sulfates. But what did that just do to our irons? How many irons do we now have in our reactants? 3. So now we need to change this number down here to 3. Okay, so now our irons are good. Our irons are messed up, but our sulfates are okay. Okay, so now you get to decide which one do you want to do next. You get to pick. There's not a right or wrong way to go about this when you choose. I'll just tell you one thing to do, a trick here. Always leave oxygen and hydrogen to the end. Usually they work themselves out. So just leave those to the end. Do everything else but them. We don't have oxygen and hydrogen here, so that's not really going to help us. So let's do aluminum. We have 2 aluminums here and 1 aluminum in our reactant. So if we multiply this one by 2, and then we take this 2 and put it up here, now we've got 2 aluminums. And that didn't wreck anything else. Didn't affect our aluminums. So now our aluminums are balanced, our sulfates are balanced, but our irons are not balanced because we have 3 over here and 1 over here. So I need to get 3 irons over here. So what can I do with this number 1? Multiply it by 3. If I multiply it by 3, I put that 3 up here, and now it is a balanced chemical equation because we have 3 sulfates on each side, 2 aluminums, and 3 irons. And it is a balanced chemical equation. So this is a way, a systematic way you can use to balance. Now, let's say you get into trouble and you're like really high with the numbers. You're like 15 or 16. Something's probably gone very wrong. It's really hard to figure out where you go wrong in balancing. So what I suggest, you start over, you just start somewhere else. So for example, we just started with sulfates. Start over, start with irons, or start with aluminums. Start with a different element or compound when you're balancing. That will help you kind of figure it out. It'll help you not make the same mistake twice. Okay. Now, if you had the balancing gene, you did that really fast. Yeah. Again, we don't like you. The rest of us are going to take 10 minutes to figure that out. You all can figure it out in 30 seconds. Just don't tell us you're doing it. So balancing can be fast, balancing can be slow. It's just kind of how your brain works. Okay, so now we're going to look at these chemical equations. So do you see these subs or these states at the back? See, this is an S, an L, an AQ, and a G. So G means gas, L means liquid, S means solid, AQ means dissolved in water. We're going to be dealing a lot with AQs, dissolved in water. But you're going to see all of these when we look at these balanced chemical equations. And we're going to learn how we figure these out as we go in the next few minutes. Okay, so first thing, I want you to balance this chemical equation. See why nomenclature is so important? Aluminum acetate reacts with potassium sulfate to form potassium acetate and aluminum sulfate. if we don't know our nomenclature, we can't even begin to start to balance an equation. So this is why I talked about in the lecture that you need to make sure you know your nomenclature because it comes up all the time. So if we look at this, acetate, oh, we need to know that's a polyatomic ion. Sulfate's a polyatomic ion. Okay, so and just for respect for time, I'm going to help you with the beginning of these. So there's your aluminum acetate, and there's your potassium sulfate. But I'm going to have you figure out the rest of them and then balance it. So I'm going to give you a minute and you can balance those and we'll finish it in just a minute. So try this and we'll go over it in just a minute. Okay, so if we look at this one, we have one aluminum on the reactants. So how many aluminums do we need on the products? 2. We have 3 acetates. 3 acetates in our reactants, but only 1 acetate here. So we're going to need a 3. So when we look at our K's got messed up there. So what do we need to put in front here? Any ideas? We need to put a 3 in front there to balance it. And then this again got messed up. So we had to change this one to a 6 to make it right. So we had 6 K's here. So this is what it ends up being balanced. Now, again, if you had to take the long way and do each one individually, that's okay. But remember, if you did that, this is one thing, this is one thing. This is a sulfate, this is a sulfate. You don't need to separate them into individual atoms because they're the same polyatomic ion and the reactant or the product. Now, if you could just look at this and you got this right without having to do that, that's the balancing gene that you have. Your homework will be very fast. Okay, so that's our balancing chemical equations. Again, the reason we balance is because we can't create or destroy matter. We have to have the same amount of matter, the same amount of atoms in the reactants as we do in the products. They're just in a different order. That's the chemical reaction. They're just in a different order. Okay, so here's one more that I want you to try. So zinc reacts with hydrochloric acid to form zinc chloride and hydrogen gas. Try this one and then we'll go over it in just a second. So when we balance this, what do we need to do with that Cl? There's 2 Cl's here and 1 Cl here. So if we put a 2 right here, we should be good. So with the nomenclature, if you're good with the nomenclature, it's not so bad. But if we're not proficient with our nomenclature, these are like, wow, hard to even start. So what we're going to be doing is we're going to be using these problems and we're going to be combining with the math, the unit conversions that you just learned. So that's why the nomenclature is so important, because without the nomenclature, we can't even write the reactants or products, which means any math or molar masses we add will all be incorrect also. So nomenclature is kind of the foundation for the rest of it. So make sure you have those polyatomic ions next to you all the time. Just have those polyatomic ions next to you all the time. Okay, so now what we're going to do is classify reactions. Okay, so now we are going to continue with 7.2, which is classifying chemical reactions. Okay, so there's going to be a couple different types of reactions that we're going to be going through. So we're going to start with combination, decomposition, single replacement, combustion, and then we're going to do some double displacement reactions. So the first thing we're going to look at is oxidation reduction reactions, shortened redox for reduction oxidation. So this involves the transfer of electrons. Most of the chemical reactions that we know of and we've seen are actually oxidation reduction reactions. So oxidation means losing an electron, and reduction means gaining an electron. You can remember it by this kind of silly little thing. We say Leo goes Gur. So when we lose, hold on, let me just go back. Lose electrons, we're oxidized. When we, that's a D, gain electrons, we're reduced. So lose electrons, oxidize, gain electrons, reduce, and we just shorten that by Leo goes Gur. And if you get to 229, we talk about Leo the red cat, and we add this and we make this a whole giant sentence that helps us for a very long time. So Leo goes Gur. So oxidation is losing electrons or an increase in oxidation number. We're going to talk about those in a second. Reduction is gaining electrons or decreasing the oxidation number. So in order to keep track of these electrons, we have a specific thing we do. We use these things called oxidation numbers. They're not actually charges. It's just a way that chemists and physicists have used to, it's like a method to keep track of the electrons. And so we're going to have to learn a few rules about this oxidation reduction. Okay. And we'll come back to this a bunch. So when it comes to assigning oxidation states, there's a few things that we need to remember. Anything by itself or in its original or natural state has an oxidation number of 0. Like magnesium, any metal, 0. Any of our Brinkelhoffs, 0. Anything in a natural state, it's a 0. If it's an ion, the oxidation number is the same as the charge. So like Na plus, it's just +1. O2 minus is just -2. Same as a charge. Same that we learned before. In a compound, always remember that group 1 always has a charge of +1, just like when we learned our ions. Group 2 always has a charge of +2, just like we learned in our ions. So far, no different than we learned before. But here's where it gets different, right here. Fluorine is always a -1. Just fluorine is always a -1. Oxygen is usually a -2, and hydrogen is usually a +1. Okay, so and group 7 often has a -1, but not necessarily. So when it comes to oxidation states, so what you need to remember is if it's by itself, it's 0. If it's group 1, +1. If it's group 2, +2. Fluorine, always -1. And then it comes to the usually. Oxygen, usually -2. Hydrogen, usually +1. Everything else can change. So those are our rules. So we're going to practice those. Okay. And they always equal 0, just like they did before. Okay, so using our rules, did you hear any rule with sulfur? Nope, which means there isn't a rule with sulfur. So you have to use another one. Was there a rule with hydrogen? There was. Hydrogen is usually a +1. Okay, so if hydrogen is a +1 and there's 2 of them, what is sulfur's oxidation state going to be here? -2, which is the same as the charge. Sometimes the oxidation state is the same as the charge. Sometimes it's not. So let's look at this next one. Okay, when we look at this one, SO3 2-. Again, there's no rules for sulfur, but what was the rule for oxygen? What is oxygen usually? Usually -2. Okay, so if oxygen is -2, and there's 3 oxygens, and the whole thing has to equal -2, what is sulfur's charge or oxidation state here? So we have this will end up being a -6 equals a -2. What is sulfur in this case? It's going to be a +4 because +4 minus 6 equals -2. So in this case, sulfur was a -2. In this case, sulfur was a +4. This is what we mean by the oxidation states can change. So you use the rules we know to figure out the ones we don't. So again, what are the rules we know? Group 1, +1. Group 2, +2. Fluorine, -1. Then we go to the usuallys. Oxygen, usually -2. Hydrogen, usually +1. Okay, so when we look at this one, let's try this one now. Okay, so what rule do we have sodium? What group is sodium? Group 1. And what's the oxidation state of group 1? +1. Okay, so sodium is a +1, and there's 2 of them. Okay, oxygen's charge is what? Or oxidation state is -2, and there's 4 of them, and the whole thing equals 0. So what is sodium's charge this time? So we have +2 and -6, and the whole thing has to equal 0. So sodium in this case, not sodium, sorry, sulfur in this case must be, you're like, what are you talking about? Sodium is +2. Oxygen will be -8, not 6, -8. And so sulfur's charge is going to be plus what? 6. So when we look at these oxidation states, so again, oxidation state, not charge. In A, sulfur was -2. In B, it was +4. And in C, it was +6. The oxidation states can change. Okay? The only ones that don't change, group 1, +1. Group 2, +2. Fluorine, -1. Oxygen, usually -2. Hydrogen, usually +1. Everything else on the periodic table can change. So when we do our oxidation states, we just need to remember those rules. Okay. Now, let's practice with these. Okay, so what is the oxidation state of sodium all by itself there? If it's all by itself, its oxidation state is 0. Chlorine, all by itself. If it's all by itself, what's its oxidation state? 0. Now it's part of an ion, so we just do it regular. So sodium will be +1. And then so what will chlorine be? -1, because it equals 0, because +1 plus -1 equals 0. Okay, now we need to figure out who was oxidized and who was reduced. So sodium went from a 0 to a +1. Okay, here's where it gets tricky. Did sodium lose electrons or gain electrons? Now remember, electrons are negatively charged, so sodium became more positive. So did it lose electrons or gain? It lost electrons because electrons are negative. So it lost electrons. And remember, Leo goes Ger. So if we lose electrons, that means sodium is oxidized, because lose electrons oxidized. Lose electrons oxidized. So sodium was oxidized. And now if we look at chlorine, went from a 0 to a -1. So chlorine became more negative. And so when chlorine became more negative, it gained electrons. So chlorine was reduced. So chlorine was reduced and sodium was oxidized. So remember when we looked at this earlier, this is when we have our sodium, which lost an electron. Here it is losing an electron. Chlorine gained an electron, and that's what created sodium chloride, right? This is actually an oxidation reduction reaction because we're moving an electron. Any reaction where electrons are being transferred, those are always going to be oxidation reduction reactions. So every time we transferred electrons when we were doing our stuff in the last few chapters, all of those are oxidation reduction reactions. Okay, so sodium is oxidized, chlorine is reduced. Let's try another one. Okay, let's try these. Cobalt, all by itself. What's its oxidation state? All by itself? Whoops, we're doing them all at the same time. All by itself will be a 0. What do we know about any of these? What is fluorine's oxidation state? It's always -1. Let's do the ones we know. Here again is fluorine, always -1. Here's copper, all by itself, 0. Okay, so now we need to figure out copper here. So if fluorine is -1, how many fluorines do we have? 2 of them. So that makes this whole side -2. So what must copper's oxidation state be? +2. So the same thing here. Fluorine is -1 and there's 2 of them, so the whole side is -2. So what is cobalt's oxidation state here? +2. So here's the same thing we just did. So the first thing we do is we identify the oxidation states. Okay, done. Got that. Check. Now we need to figure out who was oxidized and who was reduced. So I have a little help here. So if we look at here, here's cobalt started at 0 and ended at +2. So it started at 0 and ended at +2 or 2+. Did it lose or gain electrons? It lost electrons. Leo goes grr. So it lost electrons. So if it lost electrons, it must be oxidized. I'm just going to write Leo here. Lose electrons, oxidized. Now let's look at copper. Copper, that's supposed to be here with the +2, went from a +2 to a 0. So did it become more negative or more positive? +2 to 0. More negative, which means it gained electrons, and so therefore it was reduced. So I'm going to put GER, gain electrons reduced. And that's how we figure out, I'll put GER here. That's how we figure out who's oxidized and who's reduced. So in an oxidation reduction reaction, again called a redox reaction, something is oxidized and something is reduced. Something loses electrons, something gains electrons. They always go together. Something loses, something gains. Okay, now if we look at fluorine, did anything happen to fluorine? Nothing happened to fluoride. Nothing. So one thing is oxidized and one thing is reduced. Nothing happens to everything else in the reaction. They just sit there and hang out. They are not oxidized or reduced. Okay, so I want you to try this one. I want you to identify the oxidation states and then figure out who is oxidized and who is reduced. So by the way, nitrate, the whole thing is -1. This whole thing is -1. Just treat it as one thing, just as a little hint there. Okay, so try this one and then we'll go over it in just a minute. Okay, so copper's by itself, so it's 0. Silver's by itself, so it's 0. And so we just need to figure out what this copper and what this silver are. So this copper was a 0. Now it's a +2 because nitrate is a -1 times 2. So this whole side is -2. So that makes this whole side +2. Silver is going to be a +1 because this whole side's a -1. So this one is a +1. Did everybody get those two oxidation states correct? Or understand, if you did not, why? with those? Okay, then we just need to, well, I just gave you the answers. Then we need to decide which one is which. So if we look at silver, silver went from, well, let's do copper first. Copper went from a 0 to a +2. So 0 to a +2, it lost electrons, so it's oxidized. If we look at silver, silver went from a +1 to a 0, so it became more negative, so it gained electrons and is therefore reduced. Okay. How are we feeling on these? Let's take a little practice when we're working on these. So a lot of the reactions that we're going to do are oxidation reduction reactions. And so you're going to see this throughout the rest of the lecture. You're going to see these oxidation and reduction reactions. You can tell if there's an oxidation reduction reaction. The key, not 100%, but almost 100%, if you see an element by itself, and then the element is with something else, that's an oxidation reduction reaction, right? So do you see how, I'm going to choose a different color for all these. Do you see how copper's by itself and then copper's with something else? That's your hint, it's oxidation reduction. If we go back, see how cobalt's by itself and then cobalt's with something else? That's your hint, oxidation reduction reaction. Do you see how sodium's by itself and now sodium's with something else? Oxidation reduction reaction. Well, now you're going to see them all the time. So that's kind of your key. That's kind of like a clue, like, this is oxidation reduction reaction. You see something by itself and it with something else, oxidation reduction reaction. Okay, so now when we look at it, you're going to see there's a ton of oxidation reduction reactions. So these are the reactions we're going to do to start with: synthesis, decomposition, displacement, and combustion. But do you see in each of these something by itself? Now it's with something else, oxidation reduction. Something with something else, now by itself, oxidation reduction. Something by itself, now it's with something else, oxidation reduction. Something by itself, now it's with something else, oxidation reduction. So these reactions we're going to look at are oxidation reduction, and they're going to be classified into two things. So synthesis or combination, it's kind of used interchangeably, is when you have two separate things, they combine to make one. Decomposition is when you have one thing and it splits into more than one thing. Those ones are pretty self-explanatory. Single displacement is when one element is displaced. Do you see how A is all by itself here? But now it's with C. So that is a single displacement. B was with C, now it's all by itself, that's single displacement. And combustion is when anything ever combines with oxygen, and heat, that's combustion. So we're going to go through these. So first, let's look at combination or synthesis. If you look online, you hear this, you read it in the book, they're used interchangeably. Combination is synthesis, synthesis is combination. In chemistry, we just like to use multiple words for the same thing. So in this case, we're going to look at three main ones. So the reaction of metal with oxygen, the reaction with a non-metal with oxygen, and the reaction with metal and a non-metal. There's going to be a lot of different types. We're not going to look at all the individual pieces. Okay, so let's look at metal plus oxygen. And when they combine, it makes a metal oxide. So we're going to be doing this one in lab. So here you have magnesium plus oxygen combined to make magnesium oxide. Aluminum plus oxygen combines to make aluminum oxide. These are examples of synthesis reactions. And again, you can see also oxidation reduction, because magnesium's by itself, now it's not, oxidation reduction. Same thing here, aluminum's by itself, now it's not, oxidation reduction reaction also. The next one we're going to look at is a metal plus a non-metal makes a salt. Now, the salt we know is NaCl, but a salt is actually any ionic compound. So all ionic compounds are called salts. We just call NaCl table salt because it's the salt we put on our table. That's why it's called table salt. But any ionic compound is technically called a salt. So a metal plus a nonmetal is called a salt. So a metal plus a nonmetal makes a salt. And you can see also an oxidation reduction reaction. Sodium's by itself, now it's not. You can see that it's going to be an oxidation reduction reaction. So we would classify these as an oxidation reduction reaction and a synthesis reaction. So they can be classified as more than one thing. Okay, so here's our third one. A nonmetal, right? Remember where our nonmetals are? Up, top right part of our, well, you can't see this periodic table. Sorry, I will stop moving this. Top right part of the periodic table are nonmetals, plus an oxygen makes a nonmetal oxide. So all this means oxide, it means oxygen is with it. So nonmetal oxide just means that oxygen is with the nonmetal. So this makes our sulfur dioxide. So these are three main types of synthesis or combination reactions. In each of these, they combine to make one product. So that's how you can see a synthesis or combination reaction. Now, decomposition reactions are exactly the opposite. You have one thing and it breaks up into more than one thing. That's a decomposition reaction. It decomposes, it comes apart. So for example, if we have solid mercury 2 oxide, it reacts to form mercury and oxygen gas. Here we have one thing that breaks apart into more than one thing. That's decomposition, comes apart. So synthesis comes together, decomposition comes apart. But is this also an oxidation reduction reaction? Here's an element by itself, and now it's with something else. It is also an oxidation reduction reaction. It's both. Okay, so we look here, here's another decomposition, same thing. Here we have +2 to -2, just as a review. Is that oxidized or reduced? Did it lose or gain electrons? Gain electrons, so this was gain electrons reduced. This went from a -2 to 0. Lost electrons, lose electrons, oxidize. So it's both an oxidation reaction and a decomposition reaction. Okay, so now when we look at this, here's another one. Metal bicarbonates form carbonates and CO2. So here is our compound, and it breaks up into more than one thing. We're going to be doing this in lab next week. Like specifically, I think this one's on Thursday, when we're actually going to be doing this and creating this experiment in lab. So you're going to see this firsthand. It's decomposition because it makes more than one thing. Here's another one. Metal chlorates break up to make a metal chloride and oxygen. Again, one thing breaks up into more than one thing. Decomposition reaction. Okay. Here's another one. Ionic compounds decompose into their elements. So this comes apart and makes the elements. This comes apart and makes the elements. So these are 4 different types of decomposition reactions. So when you're doing your active chemistry, you can use these to kind of figure out what kind of products that you're going to make in the end. And in lab, I'll give you a little like handout sheet. It's on Canvas also, that you can use also while you're doing your homework, and you can use it during your exams too. I'll give you that in lab. Okay, so let's practice this. platinum chloride decomposes into its elements. So platinum's going to come apart into its elements. So platinum and chloride. Okay, is chlorine, is it just Cl? Remember our Brinkelhoffs? What happens when these are by themselves? They are diatomic. Only when it's by itself. Now, is this balanced? Is it balanced? We have one platinum. For chlorines, two chlorines. So what do we need to do with this 2 here? With this chlorine, we need to put a 2. Right? So here is our solution. So here's where that balancing comes in. Right? So again, those Brinkelhoffs, keep those in your brain because they pop up all semester in the weirdest places. And so this would be a decomposition reaction. Now, how we get these states, ionic compounds are usually solids. Metals are always solids, unless it's mercury. And all of these Brinkelhoffs are pretty much always gases when they're by themselves. So that's kind of how we figure out the states. Okay, let's look at single replacement reactions. So single replacement reactions, what happens is a more active metal or nonmetal replaces one that's less active. So in a single replacement reaction, they're pretty easy to see. So to see if it's a single replacement reaction, this is what we do. Do you see how zinc is all by itself here? But then a different element is all by itself? That's how you can see it's a single replacement reaction. In the reactants, one thing's by itself, but in the products, something else is all by itself. So that's kind of the clue it's a single replacement reaction. But now, how can we figure out how this reaction is going to happen? So first of all, they don't want to be all by themselves. They're very unhappy, right? Remember, everyone wants to be like a noble gas. They all want to lose or gain electrons or share electrons so they can be just like the noble gases. So when they're by themselves, they haven't lost or gained any electrons. So they're not happy by themselves. They do not want to be by themselves. They want to be with someone else. So we have a very unhappy zinc here. Zinc is like, I really want to be with chloride. Like, that would make me so happy. And so what zinc does, it says, hey, hydrogen, get out. I want to be with chloride. And then hydrogen is all by itself. Now it's not happy. That's what happens in a single displacement reaction. Whoever's stronger can kick the other one out because they don't want to be by themselves. Now, who kicks out who? Positives can only kick out positives. Negatives can only kick out negatives, right? So if you look at this, like zinc is a metal, so it's going to be a cation. Hydrogen's charge is always +1, so a positive kicks out a positive, negatives kick out negatives. We're going to continue on as we do that. Okay, so let's look at another one. So here we are, if A is a metal, because A is going to be positive, kicks out positive. It's a non-metal, negative kicks out negative. Whoops. Negative. We're going to practice that. Just remember, positive kicks out positive, negative kicks out negative. Okay, let's look at one of these. All right, in this case, we have sodium. Well, these are going to be both positives. So sodium is a metal, so it's positive. It can only kick out positive. So the question is, here's sodium. It's very sad. It wants to kick out hydrogen. It's like, hey, get out. The only way we can do this is if sodium is stronger or more active than what it's trying to kick out. This right here is called an activity series. So here's the least active and here's the most active. So the more active it is, that means it can kick out anybody else below it. So that means that these guys can kick out all of these. So what we do is we go, okay, is sodium strong enough to kick out hydrogen? Now, why did we choose hydrogen instead of oxygen? Because sodium as a metal, metals are positive. Positives kick out positives. So sodium wants to kick out hydrogen. So we look, where's sodium? Here's sodium. Here's hydrogen. Sodium is more active. So there you go. Goodbye, hydrogen. Sodium now gets to be with it. Let's look here. So is iron going to kick out copper? Or is iron going to kick out sulfate? Copper, right? So we look, can iron kick out copper? Well, here's copper. Here's iron. Is iron more active than copper? It is. So goodbye. Here's copper now, all in its lonesome, and iron gets to be with sulfate. So that's how a single displacement reaction works. If they're stronger, they can kick them out. If they are not stronger, they cannot. Okay. So these examples, by the way, are an example of a positive kicking out a positive. Metals can kick out metals. And hydrogen, because hydrogen is +1. Remember how we talked about how hydrogen doesn't really belong anywhere on the periodic table? This is, again, where hydrogen becomes positive. Metals can kick out metals and hydrogen because those are all positives. The next slide is an example of negatives kick out negatives. Okay, so when we look at this, when we look at it on the periodic table, nonmetals are always anions. So nonmetals kick out nonmetals. So in this case, is chlorine going to try to kick out sodium, or is chlorine going to try to kick out bromine? Bromine, because nonmetals kick out nonmetals, negatives kick out negatives. So the question is chlorine strong enough to kick out bromine? Well, it has to be more active. So when we look at the periodic table and we look at activities, the most active is the top, the least active is the bottom. We don't have an activity series for this because we could just use the periodic table. So the top of the periodic table, more active, bottom of the periodic table, less active. So the question is, can chlorine kick out bromine? Yep, it sure can. So goodbye bromine. And now bromine's all by itself. Okay, so again, if we look at the next one, chlorine. Is chlorine going to kick out potassium, or is chlorine going to kick out iodine? Iodine, because nonmetals can only kick out nonmetals. So chlorine has to be more active than iodine, and sure enough, chlorine is, and there's iodine all by itself now. So positives kick out positives, or you can think of it as metals kick out metals, and hydrogen, because again, hydrogen is hydrogen. And then nonmetals kick out nonmetals, or negatives kick out negatives. So either way, you can think of that one. Okay, so now here's one for us to practice. Magnesium metal is heated with iron 3 oxide. I want to know if the reaction happens, and if it does, write the reaction. So try this one, and then we'll go over it in just. We have magnesium metal heated with iron 3 oxide. So hopefully our nomenclature was on point there, Fe2O3. And the question is magnesium strong enough to kick out iron? So here's the activity series, strongest, weakest, which by the way, you'll be provided for. You don't need to memorize this. I'll give you a little handout that you can use for your quiz, your homework, your exam and such. So here's magnesium and here's iron. Is magnesium strong enough? It is indeed. So magnesium kicks out iron, and we get our equation. And of course, we have to balance it and put our states in. So any ionic compounds are always solids unless it says they're in water or solution. So that's how we know those are solids, because any ionic compound is a solid. Any metal is a solid, except mercury. So ionic compounds and metals are solids. Okay, how about this one? So iron is heated with magnesium oxide. Fe is heated with, hold on. Magnesium oxide. So we have to look. This time, our question we're asking is, can iron kick out magnesium? So iron has to be stronger than magnesium. Here's iron. Here's magnesium. Is iron stronger than magnesium? It is not. So our answer is just no reaction. So not every reaction happens. It has to be stronger. It has to be more active, right? So when you see these, don't automatically go, oh, yep, just going to write all these down. These are all the answers. Nope, you got to check the activity series. If it's not stronger, it doesn't happen. And these are the best because if your answer is no reaction, you don't have to write any states. You don't have to balance anything. You don't have to do anything. You just write no reaction and you're done. So we like the ones that are no reaction because all we have to do is write no reaction. So always check because it's less work if it's no reaction. Okay, so those are single displacement reactions. The other reactions we have, yes. Oh, right here? So when we look at this, when we write it at the beginning, here's our original reaction, but it's not balanced. So we have to balance it. So when we see this one, hold on, this is what we end up when we write it. But then we have to balance it to finish the reaction. So when you balance it, again, we could have done Mg, Fe, and O. Or when you do this, you see that there's 3 oxygens. So we put a 3 oxygen. 3 oxygens means 3 Mgs. And then when we do this, we've got 2 Fe's and 2 Fe's, but is that balanced? 3 oxygens, yeah, it's balanced. So that's why we have to balance it. Just wait a second for my computer. So that's why we had to do it in the end. And then we put our states in. Yeah, great question. So yeah, so you need to make sure that when you write these, you balance them. But again, that's why it's really nice to have no reaction because you don't have to do that. So always check. Otherwise, you go through all of the work of balancing and you didn't need to because the answer is just no reaction. Okay, so these are all, again, these are all oxidation reduction reactions on top of that because look, magnesium is by itself. Now it's with something else. So everything we've really looked at, most of them have been oxidation reduction reactions. The ones we're going to look at now are not oxidation, not necessarily oxidation reduction reactions. These ones are kind of fun. Okay, I think they're fun. You might not have the same view. So these ones are double displacement reactions. Now, double displacement reactions can break into different types of reactions. They're still double displacement, but they're just kind of like specialized. It's just kind of like when we learned hydrogen bonding, and like hydrogen bonding is just like super special dipole-dipole, but it really is the same thing. Same thing with these. Double displacement reactions can be classified as precipitation, neutralization, or gas forming, but they're all just double displacement reactions. And we're going to be doing a bunch of these in in lab next week. So in a double displacement reaction, 2 things change places. So do you see how the A is with the B and the C is with the D? Well, the A stays first, the C stays first, but the B and the D, they switched places. So two elements were replaced. Now, if you see this online, if you look at anything, sometimes it's called double displacement, sometimes it's called double replacement. It's the same thing, just books and people use different words. Same thing with single displacement. Sometimes they call it single replacement, same thing. So displacement, replacement, same thing. Okay, so in these, you're going to see that we're either going to make water, a precipitate, or bubbles. One of these things are going to happen. A precipitate, remember, is just a new solid. So there wasn't a solid, now there is a solid. That's a precipitate. We mix two liquids and we make a solid. That's a precipitate. Okay, so here's an example of a precipitation reaction. So we have barium chloride, which is an AQ, that means it's a solution. Sodium sulfate, AQ, that's a solution. So we had two solutions, but when we mixed them together, we made a solid. That is a precipitate. It's abbreviated PPT for precipitate. So we have two liquids, we mix them together and we make a solid. That's a precipitate. And this is a double displacement reaction. So when we see this double displacement reaction, do you see how barium is first? It stays first. Sodium is first. It stays first. But the chloride and the sulfate switched places. That's what a double displacement reaction looks like. The second two switch places. Okay. So let's try this. So again, solubility is just the maximum amount that can be, we're going to look at solubility. It's the maximum amount that can fit in a solution. So if it dissolves, we call it soluble. So soluble means it dissolves. If it makes a solid, we call that insoluble. So a precipitate is a solid, and that is insoluble. A soluble means it's an aqueous solution. So soluble means aqueous. Insoluble, we'll see it'll be a solid with an S. So S means solid, AQ is soluble. So you're going to see these on our double displacement reactions a bunch. Precipitate, solid, insoluble. So if it's insoluble, that means it's an S. Soluble always means AQ. That's a Q, okay? So there's this thing called a solubility table. You're not going to need to memorize it, but you are going to need to use it. It comes in a bazillion different forms, and they're all the same rules, but they just state them differently. Some solubility tables are like 4 pages long. We're not really going to use that one. Active has its own solubility table when you're doing your homework, so you can use that solubility table. The one we'll use on your quizzes and exams will be kind of a shortened solubility table, so you don't have to be looking for all the rules. So how a solubility table works is it tells you what will be soluble and what won't be soluble. So this one says soluble, and again, remember soluble means AQ. AQ. Insoluble means S, solid. So let's look at this. So all group metals are soluble. They're AQs. The halide ions, what group is, who's the halides? What group is that? Who's the halogens? Group 7. So all the group 7s are soluble except, this is where the exceptions, Ag. So this means like AgCl would be a solid. Hg and PbCls would be solids. These are all soluble, no exceptions. sulfate is soluble except if it comes in the form of one of these. So like BaSO4 would be a solid. Insoluble compounds, which means these ones are all going to be S's now, and these are their exceptions, which will all be AQs. So hydroxide is soluble, like NaOH is soluble. Oops, is insoluble. Let me just do one that's insoluble, not group 1. CaOH2 is insoluble. But if it's group 1, it is soluble. NaOH would be AQ. So this is how you use the table. We're going to practice this because it's a little tricky the first time you see it. So let's practice. In the tables, I'm going to show you a couple different forms of the table so you get used to using all the different forms of these tables. This is the one from your book, but I'm going to show you the one that Active has and the one we use also. Okay, so before we go to this, we need to learn what the word dissociation means. So in your homework, you're going to see a lot of things that say, write the dissociation equation. What does that mean? That means if it's soluble, split it up. If it's insoluble, don't. So this says AQ. So you split this up into calcium and 2 chlorides. This says AQ. So it separates into silver and nitrate. This says AQ. So it separates into calcium and 2 nitrates. This says solid. So it does not come apart. So when you see the questions, write the dissociation, we look at the solubility table, and if it's soluble, you split them up. If it's insoluble, you don't. Keep them together. Okay, so let's practice this. We're going to try one of these. So here's our reaction. I'm just going to write the whole thing here because it's going to be too much to try to do on our own. Okay, so this is a double displacement reaction. So whoever's first stays first. So the PB stays first. And the K stays first. Now, why is this 2 here? The 2 is there because lead's charge is +2 and nitrate's charge is -1. So that 2 is there to balance the charge. So we're not going to necessarily take it over to the other side. Why is this 2 here? Because chromate's charge is -2 and potassium's charge is +1. So it's there to balance the charges. It's not there as a permanent, it's not there permanently. Now, why is this 3 there? Because it's part of the polyatomic ion nitrate. So when we switch these ions, we're not going to take the coefficients, or we're not going to take the subscripts. We only take the subscripts of the polyatomic ions. So when we exchange these ions here, it's PB, PB, CrO4, and K, NO3. I did not take this 2 and I did not take this 2. The reason we don't take them is because they were there to balance the charges. So remember when we did nomenclature and you had to do like your crisscross or your algebra way? That's why those were there. We don't take them because we might not need them. So if we look at our charges, PB is +2, chromate is -2, K is +1, and nitrate's -1. Do I need to balance those charges? We do not. We don't need those coefficients. We don't need them. Is our reaction balanced? We have 1 PB, 1 PB, That's balanced. 2 nitrates, 1 nitrate. So how do we balance this KNO3? To put a 2 in front of it. Okay. And then we have 2 Ks, 2 Ks, 1 chromate, 1 chromate. It's balanced. So again, if you need to do the long way to balance, you can. That's just the short way that I just did right there. But it's whichever way works best for you. Okay, now we need to figure out, are one of these a solid? Okay, so we're going to go back to this solubility table. So we're going to look at lead chromate or potassium nitrate. We're going to see if one of those is a solid. So let's look for nitrate first, or potassium. Okay. Oh, group 1 and nitrate. These are both soluble, which means AQ. So if we go to our problem, this is soluble, AQ. Okay, let's look for chromate or lead. Do you see chromate anywhere here? Oh, there's the word chromate. It's insoluble unless it has a group 1 metal or ammonium. That is not a group 1 metal or ammonium. So therefore, this is our solid. And so this would be our balanced chemical equation. That is our precipitate. So that is our precipitate or our solid that we have, which is different than these are all aqueous. Oops, I already put aqueous on that one. This is a double displacement reaction. So in our double displacement reaction, it's a precipitate. We made a solid, and the solid is potassium chromate. Okay, so we're gonna look at this again. Not by zooming in. There we go. Okay, so the first thing we did was we exchanged the ions. This is all going to come back here again. So the first thing we did is we exchanged the ions. We switched the second ones. And then we balanced our charges to make sure everything worked. In this case, we didn't have to do anything. And then we balanced our equation. And then we determined our solubilities using our solubility table. And we put in our states. So in a double displacement reaction, this is what occurs every single time. We do this again and again and again. Okay, so the next thing we have is net ionic equations, but that's like a whole big brain thing. So I think we're going to take a break on that. Yeah,